Hello, Storlytics user. Hope you're having a great day. We are coming to you with another video to help simplify your energy storage needs. Today, we're going to be looking into the Defined System module of Storlytics 0.3.0. We'd also like to mention that in the future version of Storlytics software, the Defined System module will be referred to as the Battery System Modeler. Defined System Module, or in the future versions, Battery System Modeler in Storlytics, allows users to perform simulations based on an expected battery response for various battery energy storage applications. First of all, we will have to launch the Storlytics software. That can be done either through a shortcut icon in the desktop or through the Windows Start menu. Once we launch the software, our landing interface for the software would look something like the one we're seeing on the screen right now. And by default, we can see that the Storlytics software will open in Defined System Module interface. Before we get started on the demo, the Storlytics user will also find a document of this tutorial by clicking Help and DSM Tutorial. This document should walk you through the basics of using the Defined System module. Today, we're going to look into an example of using the Defined System module to design battery energy storage system to maintain point of interconnection power requirements. The point of interconnection requirements could be based on various use cases for battery energy storage system, including PV smoothing, frequency regulation, energy arbitrage, peak cloud shaving, and so on. Now let's look into how to load an example case to the Storlytics workspace. For that, click on File, Open, which by default opens Storlytics user files, and under Projects, you can see a couple of example cases that is provided with the software. In this case, we're going to look into example_case_dsm.saj, which is the tutorial project for the Defined System module. Also note that the file extensions for Storlytics projects are .saj. Once we load this example case into the Storlytics workspace, we can see the project name on top, which the user can define or edit. So let's make it _test. By default, the file name is the name of the file that was loaded in the workspace. Also, a point of interconnection power profile has been loaded under the user definitions interval data. The point of interconnection power profile considered is based on a peak load shaving application. A separate video will discuss on how to develop and provide point of interconnection power profile based on the use case of interest to the user. For now, let's look into different tabs under user definitions to understand the various inputs that the user needs to provide for DSM use cases. The user definition sections defines various inputs the user has to provide to design the battery energy storage system for the application they are considering. In this particular tutorial, we are considering a peak load shaving application for which we have already provided a point of interconnection power profile. If the user was to change the profile, they can do so by clicking on the POI profile and selecting a different file that has an updated POI power profile. Under the Equipments tab, the user can specify the battery and inverter model that they are considering. The user has an option to choose from various battery and inverter models provided with the Storlytics library based on the battery chemistry and the application they are considering. Or, the user has the option to specify or design their own battery model by clicking on the eye icon, which opens the Storlytics Components editor, in which the user can provide various information of the battery they are considering by providing data for the battery cell information, module information, the user has the option of providing degradation parameters if they want to include degradation in their simulations. Similarly, for the inverter model, the user can choose from the various generic inverter models that are available in the Storlytics library, or the user can specify or design their own inverter model by clicking on the eye icon. This opens the Inverter Component Editor, and the user can define their own inverter model by specifying various parameters in the DC/AC Information tab, Efficiency Table, Temperature derating data, and so on. Also, users can use the OND files, which are used in solar system simulators like PV-SYST, to specify inverter rating. A separate video will cover on how the user can define the battery model, as well as the inverter model for the use case they are considering. Now let's look into the System Specifications tab. This provides base information of the battery energy storage system that we are considering. The first input is the number of modules in the series per rack, so this can be seen in the system configuration diagram on the bottom right. We have battery modules connected in series to form a battery rack and multiple battery racks in parallel connected to the inverter system. So, the user has to specify the number of modules in the series per rack, number of racks per inverter, the total number of inverters for the use case. The user also has to specify copper and core loss for the interconnection transformer that they are considering, and any auxiliary losses that might occur within the battery energy storage system. Under the Operations Limit tab, a user can specify the operating range of the battery. Finally, let's look into the Battery Degradation tab. Battery degradation will be included in the studies only when the battery degradation checkbox is selected. If not selected, the battery degradation studies will not be included in the final report for the simulation. A separate video will cover on how Storlytics can be used for the battery degradation studies. For this tutorial, we will not consider the degradation studies, hence we unselect the checkbox. Once the user specifies all the parameters for the battery energy storage system that they are designing under user definitions, the Sizing Assist section allows the user to analyze whether the designed battery energy storage system is sufficient for the POI profile, as well as the energy requirement at the point of interconnection. For now, based on the inputs provided by the user under the User Definition tab for interval data, equipment models, system specifications, and so on, we now have a battery energy storage system that has an inverter that can supply up to 5,500 kilowatts and a battery with an energy capacity of 12,718 kilowatt hour. The POI profile section under Sizing Assist allows the user to calculate father energy and power requirement based on the POI power profile provided. This is computed by the Storlytics software when the user clicks the Calculate Energy and Power Requirement button. The computation output calculates the maximum charging/discharging power and the maximum energy charge/discharge per day based on the POI power profile provided by the user. The user has to compare the POI power profile energy and power requirement with the battery energy storage system, inverter system, as well as the battery energy requirement that they have designed. Once we ensure that the battery energy storage system that we've designed satisfies the point of interconnection power profile requirement, we can run the simulation which analyzes the performance of the battery energy storage system that we designed. For this, click on Run. Once the simulation run is complete, we can see the action statement on the status log saying, DSM simulation completed successfully. Next, we can generate the report of the simulation by clicking on the Generate Report button at the top right corner. This document will open on the default PDF reader. The report compares the performance of the design battery energy storage system based on the needs of user specified within the point of interconnection power profile. Now let's quickly review the report generated by the Storlytics defined system module simulation. We will have a separate video in which we will go into the details of various analytics. For now, let's look at the outputs within the Storlytics simulation reports. This section of the report presents the user-specified system specifications of the battery energy storage system. This includes the inverter battery selections and respective ratings, loss assumptions, and operational constraints. Storlytics also provides various analytics, including the power achievement analytics, in which we can see whether the power dispatch requirements has been met by the designed battery energy storage system. It can also look into the energy dispatch of the design system versus the total energy requirement based on the POI profile. In this peak load shaving use case example, the power dispatch requirement is completely met by our design, but the energy requirement in certain areas has not been met. The report also presents the different system losses, including the charge and discharge efficiency, and the total round-trip efficiency of the design battery energy storage system. This section showcases the daily charge-discharge throughput, cycles, and the daily state of charge range of the battery based on the POI profile provided. Storlytics also provides a summary of the daily range and average of battery C rate. Finally, the report specifies the system capacity summary and the energy flow diagram, which shows the flow of energy within the battery energy storage system and the details of the losses that occur in the different sections of the battery energy storage system. As you can see, that Storlytics software provides a highly detailed analysis of the battery energy storage system designed for the application the user specified using the POI power profile. It provides the user flexibility to analyze and design the various components within the battery energy storage system. With that, we would like to conclude this tutorial on the DSM module. Please keep an eye out for additional videos describing other features, functionalities, and updates on the Storlytics software. We hope Storlytics and this tutorial will help simplify your energy storage needs. Thank you and have a great day.